welcome to True Projects. In this video, we are going to explain about the project entitled as GeoDisasterAINet, an explainable deep ensemble framework for real-time urban and rural disaster classification and resilience. So before getting into the video, let me give you the brief description about the project. GeoDisasterAINet is an advanced AI framework that combines multiple deep learning models to classify disasters in both urban and rural areas in real time. It's designed to be explainable, helping communities understand risk and enhance disaster resilience. Coming to the abstract, GeoDisaster AI Net is an advanced AI system designed to detect and classify disasters in both urban and rural settings in real time, helping authorities respond more effectively. It collects and analyzes data from multiple sources, including satellite images, sensor networks, and social media to ensure accurate disaster identification. The framework combines several powerful machine learning techniques such as convolutional neural networks for image analysis, transformer models for sequential data understanding, and gradient boosting ensembles for robust predictions, allowing it to perform well across diverse environments. One of its standout features is explainability. Using attention maps and interpretable feature attribution, the system shows why a particular disaster prediction was made, helping emergency personnel make informed decisions. Additionally, GeoDisaster AINet is designed for fast processing, scalable deployment, and actionable insights, making it a particular tool for improving disaster preparedness, mitigation, and recovery strategies. Coming to the existing system, existing disaster classification systems are generally built around single model approaches or depend heavily on manual monitoring and limited remote sensing technologies. Because they often process only one type of data at a time, such as satellite image, sensor readings, or textual reports, they struggle to combine multiple data sources for a complete and accurate understanding of rapidly changing disaster situations. This limitations makes real-time response difficult, especially in dynamic environments like floods, wildfires, or earthquakes. Moreover, many traditional machine learning models functions as black boxes, offering little interpretability, which reduces trust among decision makers who must act quickly during emergencies. Another key weakness is that these systems are usually designed for either urban or rural areas, but not both, leading to reduced performance when applied across different geographical settings. Coming to the proposed system or base paper work, the proposed GeoDisaster AI Net framework is an advanced disaster classification system designed to overcome the limitations of traditional models by integrating multiple intelligent components into a unified architecture. It uses a deep ensemble approach that combines convolutional neural network to extract critical visual features from satellite and UAV imagery, transformer models to analyze sequence data from IoT sensors, and gradient boosted classifiers to fuse them diverse data streaming into a final, highly accurate decision. The system supports real-time data ingestion, enabling it to process satellite feeds, drone images, sensor measurements, and even crowded source textual reports simultaneously, which ensures comprehensive situational awareness. To build trust and transparency, GeoDisaster AINet includes an explainability module that applies sharp values, attention heat maps, and interpretable feature profiling to clear show why a particular disaster classification was made. Additionally, its flexible deployment capability across cloud, edge, and on-premises platform ensures scalability, fast response time, and adaptability to both urban and rural environments. Overall, the proposed system delivers accurate, explainable, and real-time disaster classification to support effective and timely decision making by emergency management teams. Coming to the dataset, the Kaggle Natural Disaster Image Dataset contains more than 5,000 labeled images representing four major disaster categories: cyclone, earthquake, flood, and wildfire. The dataset is organized into separate folders for each disaster type, where Images are implicitly labeled based on their directory placements, making it straightforward for superior image classification task. It consists solely of raw images without additional metadata such as timestamps, geographical coordinates, segmentation mask, or severity annotations. Because of its clear structure and moderate size, the dataset is well suited for training convolutional neural networks, conducting transfer learning experiments, and supporting academic research or demonstrating projects related to disaster recognition and environmental image analysis. However, its lack of multimodal information limits its uses primarily to baseline image classification applications rather than advanced stimulation awareness system. Coming to the novelty or extension or enhancement or improvement. First, as an extension, the original image dataset was pre-processed and converted into NumPy arrays to make it suitable for deep learning models. The class labels were transformed using one-hot encoding, which allows the models to treat each disaster category as a separate output class for accurate multi-class classification. Three deep learning approaches were implemented to compare exception, ResNet 50, and a hybrid ensemble model that combines predictions for multiple networks. Among this, ResNet 50 achieved the highest test accuracy of 99.2%, indicating superior feature extraction and classification performance on disaster dataset. Furthermore, to improve transparency and interpretability, explainable AI techniques were applied. GradCam was used to generate heat maps that visualize, highlights the important regions of an image influencing the model's prediction. Additionally, Line was implemented to provide local explanations, helping users understand how specific image features contribute to a particular classification results. Furthermore, a user-friendly web application was developed using the Flask framework. This interface allows users to upload an image, after which the trained model processes it and provides a disaster type prediction along with interpretability outputs, making the system accessible for real-time practical use. Coming to the flow of the work, first, we need to import the packages. In this step, all the necessary Python libraries required for data processing, visualization, model building, evaluation, and deployment are imported to prepare the work environment of the project. Next, exploring the dataset. The dataset is loaded and examined to understand its structure, number of classes, number of images per category, and overall data distribution to ensure it is suitable for classification. Next, data pre-processing. In data pre-processing, we have image resizing, normalization, and label encoding. Image resizing. All images are resized to the fixed dimension so that they can be consistently fed into machine learning and deep learning models. Normalization. Pixel values are scaled to standard range to improve model training stability and performance. Label encoding. Textual class labels are converted into numerical formats so that algorithms can process them efficiently. Next, data visualization. Data visualization consists of distribution of classification outcome and sample images for each class. First, distribution of classification outcome. A graphical representation is created to show how images are distributed across different disaster categories. Next, sample images for each class. Representative images from each disaster class are displayed to visual verify correctness and diversity of the data set. Next, build the classification models. In this stage, three baseline feature-based models are developed to extract structure disaster related features and perform initial classification. Stage 2, class imbalance is handled using SMOT and features are standardized using standard scalar to improve performance. The process features are then classified using XGBoost, combined separately with ERI 2025, DRI with 2025, and DE with 2025 to enhance prediction accuracy. Coming to the stage 3, in this stage, XGBoost predictions are further refined using a multi-class support vector machine to improve decision boundaries and increases classification robustness. Coming to the extension, the dataset is converted into NumPy arrays and labels are one-hot encoded and compatibility with deep learning models. Advanced CNN architectures such as exception and ResNet 50 are trained. And the hybrid ensemble combining both models is implemented to achieve higher classification accuracy. Next, Comparing the models. All developed models are evaluated using standard performance metrics to objectively compare their effectiveness and reliability. Next, comparison of graphs. Visual graphs are generated to present and compare the performance scores of all the models, making it easier to identify the best performing approach. Next, save the best trained model. The model that achieves the highest performance is saved for future use and deployment in the real-time application. Next, explainable AI visualization. To improve transparency, Lime is used to explain individual predictions, while GradCam generates heat map to highlight important image regions, influencing the model's decision. Next, Flask web app. The web application is developed where the front end allows users to upload the image and the backend processes the image using the trained Ensemble model. The system then displays the uploaded image along with the predicted disaster type and confidence score, optionally including visual explanation overlays. The algorithms used are stage 1, we have used ERI 2025, DRI 2025, and DE 2025. Coming to stage 2, we have done the SMART and standard scalar and we applied on the models along with the XGBoost. In the stage 3, we used standard scalar and the model we have used XGBoost plus multi-class SVM. Coming to the extension, we have converted the data into NumPy arrays and we have applied one-hot encoding labels for the models, which includes exception, ResNet 50 and hybrid ensemble model, which combines exception plus ResNet 50. Coming to the requirements, we have both hardware requirements and software requirements. Hardware requirements consist of operating systems Windows only, processor i5 and above, RAM 8 GB and above, hard disk 25 GB and above. Software requirements consist of application framework Anaconda, primary language is Python, front-end framework is Flask, backend is Jupyter Notebook, database is SQLite 3, technologies which we use to build the front end are HTML, CSS, JavaScript, and Bootstrap 4. To execute the project, first we need to open the project code folder which contains the project source code files. This folder is a complete package of your project's code base containing everything needed to develop, test, and deploy your application or model. Static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. Templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represents different pages of the website. App.py file. This .py file contains the information related to front-end logic. It could include code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. Models. These are the model files which contain algorithm information which will be loaded into the project code during the runtime. IPYNB files. These are the Jupyter Notebook files which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute the code in individual cells, making it a popular choice for data science. Signup.db file. This file is a database file used to store the user information. Coming to the execution of the project, first, you need to copy the path of the code folder from the address bar of the file explorer. Then, open Anaconda prompt. Use the command cd followed by a space and then paste the copied path. This command is used to change the current directory to the code folder's path. Now, compile the app.py file using the command python space app.py in the Anaconda prompt. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address with the port number of 5000. Copy the link provided by the framework and paste it in any web browser. I prefer Chrome. So now, the home page of the project should be displayed in the browser. This is a front-end build using the Flask framework. In this page, we have Home button, User Login Here button, and Register Here button. Firstly, click on Register Here button so that the user registration form will be opened where you need to enter the details and create an account for user authentication like username, full name, mail ID, mobile number, and a strong password. Then click on sign in, so that all the given details are stored in signup.db, and the login.html will be opened, where you need to access the application with the help of username and password. Click on sign in, so that the prediction page has been displayed. In this page, we have prediction button, graphs button, and notebook button, along with logout button. Firstly, click on prediction button, so that the upload image form will be opened, where you need to upload the disaster image and predict the disaster type. Here we have how it works, like the application of working. Now let us upload an image here. First, the image has been successfully uploaded. The preview of the image can be seen below. Now click on predict the disaster type button, so that the given input image will be pre-processed and the prediction will be displayed. The predicted results are cyclone for the given image, and the confidence score is of 100%. And here we have the safety measures and recommended actions. And this is the original image which we have uploaded. And this is a GradCam heat map image. And this is GradCam overlay image. And this is a line explanation image. Now click on predict other image, so that the form will be opened, where you need to upload the image. The image has been successfully uploaded. Now click on predict disaster type, so that the given image is pre-processed and the predicted class will be displayed as earthquake. The predicted class is a earthquake. The confidence score is of 100%, and we also have the safety measures and recommended actions. And this is the original image which we have uploaded, and this is a GradCam heat map image, and this is GradCam overlay image, and this is line explanation image. And now let us click on predict another image, so that the prediction form will be opened, where we need to upload an image. The another image has been successfully uploaded, and now click on predict disaster type, so that the given image is pre-processed and the predicted class will be displayed as flood. The predicted class is flood. The confidence score is of 100%, and for this image we have the safety measures and recommended actions. And this is the original image which we have uploaded, and this is GradCam heat map image, and this is GradCam overlay image, and this is line explanation image. Now click on predict another image, so that the prediction form will be open, where you need to upload an other image. The other image has been successfully uploaded. Now click on predict disaster type, so that the given image is pre-processed and the predicted class will be displayed as wildfire. The predicted class is wildfire. The confidence score is of 99.99%, which means almost to 100%. And for this, we have the safety measures and recommended actions. This is the original image which we have uploaded, and this is GradCam heat map image, and this is GradCam overlay image, and this is line explanation image. As the natural disaster dataset has been divided into 4 different disaster types, like wildfire, flood, earthquake, and cyclone. We have seen all 4 outputs. Now, click on view analysis, which means the graphical representation of the project will be open. Now, let us check one by one. First, we have image count per class graph. The bar graph shows the distribution of image across 4 disaster classes in the dataset. Earthquake has the highest number of images, while cyclone has the lowest. Flood and wildfire have nearly equal representation, indicating a relatively balanced dataset with slightly variation among the classes. And next we have confusion matrix and ROC curve graph. The confusion matrix shows that the hybrid ensemble model correctly classifies almost all images in each disaster category, with very few misclassification across cyclone, earthquake, flood, and wildfire classes. The ROC curve indicates an AUC value of 100% for all classes, demonstrating excellent classification performance and near perfect separability between the disaster category. And next we have training accuracy and loss graph. The training accuracy steadily increases and remains very high, while validation accuracy also stays consistently strong. Next, we have training accuracy and loss graph. The training accuracy steadily increases and remains very high, while Validation accuracy also stays consistently strong, indicating effective learning with minimal performance fluctuations. The training loss decreases over epochs, and although validation loss shows slightly variation, it remains relatively low. Overall, the graph suggests that the hybrid ensemble model achieves highest performance with no significant overfitting. And next we have accuracy by model graph. The bar graph compares the accuracy of different machine learning and deep learning models. The deep learning models, particularly ResNet 50 and hybrid ensemble, achieve the highest accuracy, outperforming the ERI, DRI, and DE combined models. This shows that the ensemble and CNN based approaches provide superior classification performance. Next, we have F1 score by model graph. The graph compares the F1 scores of different models, showing that deep learning models achieve the highest performance. ResNet 50 and the hybrid ensemble obtain F1 score closely to 0.99%, indicating excellent balance between precision and recall. The ERI, DRI, and DE combined models perform slightly lower but still maintain strong classification effectiveness. Next, we have recall by model graph. The graph shows the recall values are highest in the deep learning models, particularly ResNet 50 and hybrid ensemble, reaching close to 0.99%. This indicates their strong ability to correctly identify disaster instance without missing many true cases. The ERI, DRI, and DE combined models have slightly lower recall but still demonstrate solid performance. Next, we have precision by model graph. The graph indicates that precision is highest for all deep learning models, especially ResNet 50 and hybrid ensemble. With values close to 0.99%, this shows their strong ability to correctly predict disaster classes with very few false positives. The ERI, DRI, and DE combined models also achieve good precision but slightly lower compared to CNN based approaches. And finally, we have SHAP analysis graph. The graph represents a SHAP value visualization showing how different features contributes to the model's prediction. The color scale indicates positive and negative impacts on the classification outcome, though the contributes appear very small. This suggests that individual feature effects are subtle but collectively influence the final prediction. And then click on logout. So finally, GeoDisasterAINet presents a robust and scalable deep ensemble framework designed for accurate real-time disaster classification across both urban and rural environments. By integrating multimodal data source with advanced deep learning models and explainable AI techniques, the system ensures high predictive performance along with transparent decision making. It develops flexibility across cloud, edge, and on-premise platforms, enhances responsive duration, critical situation. Overall, the framework strengthens disaster resilience by enabling faster, more reliable, and interpretable support for emergency management teams. So, this is all about your project. Thank you.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.